Let's tackle another example of complex motion in a multi-particle system by using the energy principle. First, by applying it to a simplified point particle model, and then to the full multi-particle situation. Here's the problem statement. Two blocks, each of mass 5 kilograms, are connected by a spring of negligible mass and held up vertically, one block over the other as shown. Starting from rest, an upward force of constant magnitude, 167 newtons, is applied to the top block. Sometime later, the blocks have moved upward. Labeling the bottom block as block 1 and the top block as block 2, the initial and final heights of the two blocks are given as shown. Choosing the system as the two blocks and the spring, find the final translational kinetic energy of the system and the change in vibrational energy of the system. Drawing sketches as we go along will help us visualize the situation. We also note here that interactions on the system also include the weight forces exerted by the Earth on each block. We're asked to find energies in this problem, so we start with the energy principle. Moreover, since we're first asked to find the final translational kinetic energy, we will apply the energy principle to the point particle model, which means we'll need to find the location of the center of mass for the system. We know how to do this, so let's do that calculation here. We're going to keep our results in symbolic form and plug in numbers at the very end. Let's now apply the energy principle to the point particle model, which can be visualized like this. Notice the weight forces show up here as one force, the total weight force, F sub g total, and that all interactions in the point particle model act at the center of mass. Our energy principle for this looks like this, where the total energy change, delta E, in the point particle model only includes the change in the system's translational kinetic energy, delta K trans. Now, delta K trans is K trans final minus K trans initial. However, since the system is initially at rest, the initial translational kinetic energy is 0. So, the change in translational kinetic energy is just equal to the final translational kinetic energy, which is one of the quantities we want to solve for. So to do this, we need to find the total work done by all the interactions acting through the center of mass displacement. Here we use the subscript pp to remind us that this is the work calculated in the point particle model. Since both forces here are constant, we find the work by taking the scalar product of each force with the center of mass displacement. When we do that and plug in all the known values, we can solve for the final translational kinetic energy as we show here. Now we're ready to find the total change in vibrational energy, delta E vib. This includes both the change in spring potential energy as well as the change in the kinetic energy of vibrations, oscillations relative to the center of mass. This is an internal energy change, and so this would be counted as part of the total energy changes in the energy principle applied to the full multiparticle model. We also include here the change in translational kinetic energy, which is the same as we found in the point particle model, so we know what that is. Now, when we solve for delta E vib in the energy principle, we see that we need to compute all the work done on the system by the surroundings. There are 3 separate work terms here. For the top block, block 2, there are 2 work terms, work done by the upward pulling force and work done by the weight force, F sub g on 2. While for the bottom block, block 1, there is only one work term, the work done by the weight force, F sub g on 1. Notice the effect of the spring on both blocks is already accounted for by delta E vib, so we don't have any spring force to include here. Also, there is no gravitational potential energy. The Earth is not part of the system, and the Earth's effects on the system are already accounted for by the work terms involving the weight forces. Let's calculate each of these work terms. The displacement of block 2, which has a magnitude equal to the magnitude of delta y2, is the correct displacement to use for computing the works done by both forces on the top block. So we use that to compute these work terms by computing the appropriate scalar product to end up with this result. The displacement of block 1, which has a magnitude equal to the magnitude of delta y1, is the correct displacement to use for computing the work done by the weight force on the bottom block. So we use that to compute the work with the appropriate scalar product, and we end up with this. Notice that the center of mass displacement is not used at all in the multiparticle system because none of the forces actually act through that displacement in the multiparticle system. We add all these works together to get the total work done on the multiparticle system, and this is the result in symbolic form. We can now insert this into the energy principle, and we can solve for our last unknown, the change in vibrational energy. To do this, we insert the numerical values, and we include the result for the change in translational kinetic energy that we found earlier. We notice that the change in vibrational energy is positive. We see in this case that there is net energy transfer from the surroundings to the system, and some of that transferred energy shows up as an increase in vibrational energy. Just a quick final note here. We don't know how much of the vibrational energy is kinetic and how much is spring potential energy. To understand this, we would need to know more information that isn't provided in this problem.